So thank you for attending. I present you this work. So this is a joint work between a hardware team and a software team. And well, it is a collaboration between the two teams. And I try to show you what we have done in TLA. First, we have already presented last year, well, what they call the hardware context. That is, we have understood the problem with the hardware team. This is what we call the hardware context. And we have done some studies, especially with the hardware context. And since then, we have better understood the problem. And we have tried to come with what we would call a software model that we better understand. And consequently, well, some proofs have already been done, but now, since we possess this software model, we believe that we are going to proofs that are more understood, that we can more understand than before. So we have now, in this part, we have what I would like to say, a proof engineering part that is more consequent and from our software point of view, much more interesting than it was before. So this understanding has led us towards an abstract pipeline model. And this abstract pipeline model relies on a generic architecture model and basic pipeline properties. And last, I try to draw some conclusions and perspectives. So just to recall the hardware context in which the work has been led. So we are working with a hardware team, and this hardware team is especially interested by real-time architectures. And in this context, they are mostly interested how to calculate efficiently and with the scaling approach the worst execution time. So this is their main objective, is to come with architectures on which it is possible to calculate efficiently the worst calculus execution time. So in order to have that, we must have some architectures that have good properties. And when you have anomalies, the calculus doesn't go with the architecture, in the sense that you can have a better architectures, and the calculus, the WCET that you calculate will be worse. And if you have that, you cannot reason efficiently, because you cannot rely on the monotonicity of your architecture. And this is why this team is looking for architectures with a good property, that is monotonicity property. So this was the architecture part, and now I'll try to explain the software part and how we have understood their model and how we have modeled it. And as I have said, from our point of view, this is much more interesting, since we have a better software model, and then the proofs can be more easily explained and conducted. So I'll present what we call a system view. And as we have seen before, for this system view, we can consider that we have two levels. We have an untimed level without time, and then we have a timed level in which we introduce time. And then we obtain the properties by reasoning on these two models, the untimed model and the timed deterministic model. So just I recall what we understand by the architecture, the static architecture features and the dynamic architecture features. So with respect to the static architecture features, as we have seen just in the preceding talk, we consider the pipeline as an acyclic graph of stages. Each stage has a capacity and a latency, and the memory access is exclusive. That is, the stages will compete for the memory stages, and this access has to be exclusive. With respect to the dynamic features, we consider that a program is a sequence of instructions each instruction has a path over the pipeline, and each instruction has its own latency with respect to each stage. Its own latency, because depending on the instruction, it will make a cache miss or a cache hit, and this gives for each instruction its own latency. So, for instance, in the architecture, the hardware team has the following architecture, and he is working on this architecture. So what we see is, we see the graph. This is an acyclic graph going from the pre-stage to the post-stage. Each stage has its capacity, which we should not overload. And among these stages, we have some stages that access to memory. For instance, we have the instruction fetch stage, which access to memory. We have the load stage, and we have the store stage, which access the memory. And of course, since they access the memory through a unique bus, this access has to be done in an exclusive way. We have also some special nodes. For instance, here we have the insert stage, which forwards the instruction to the concerned functional unit. And here we have the commit stage, which after the instruction has been processed, take the instruction and commit it. If we want the result of the program to be correct, this commit has to be done in the order of instructions. This is important because here the things are done in a concurrent way. So the order that has been seen here is not that the order is not necessarily the same, that the order that will be seen at the commit stage. So this order must be recovered explicitly by this stage in order to forward the instruction to the store stage, and in order that the store be done in the order of the instructions. Just an example how we proceed. So at each stage, we have what we call a running instruction, and we have a FIFO of instructions, that is the instructions that are waiting to leave to the next stage. For instance, here in the pre-stage, we have no running instruction, and all the instructions of the program are in fact waiting to leave, to go to the next stage. Here we have the instruction stage, and here we have a unique running instruction, number 1, and the FIFO is empty, and the pipeline is still quiescent. Much of the stages are empty, and their FIFO are empty. What do we do then? What we do is that we have to make the instructions move along the pipeline. And of course, this has to be done by respecting certain rules. So we have to respect the capacity of stages. The move must be in order of the instructions. As we have seen precedently, we can have some concurrent things done inside the pipeline, and then we must recover the order at the commit stage. We must respect stage exclusion with respect to memory. We have no preemption, so we cannot interrupt an instruction. And also, this is a basic property of the architecture, the move must be maximal. Is that if there is some stage that is free and an instruction needs to go to that stage, it has to go to that stage. This is what we call the move must be maximal. And also, since we are going to make time calculus, the model that we would like to exhibit must be deterministic. So again, here, for instance, how it works. So here, what we say the untimed model is that we do this in a non-deterministic way. We choose, we select a subset of running instructions, and we make this, these instructions can be called victims, and we make these instructions move in the way that I have just talked about to the next stage. So, for instance, here, precedently, we have only one running instruction. It was 1. So 1 is selected as the victim. 1, since it's FIFO, it's empty, we leave the instruction fetch stage to the instruction search stage. Since it has left the instruction stage, the instruction fetch stage becomes free, and then the instruction 2, that is the first instruction in the pre-stage, will leave the pre-stage and move to the instruction fetch stage. And this is how the pipeline works. And well, we can also develop the other example. So all this, as I have said, is done in an untimed way. And how do we have now the timed way explicitly with respect to the model? In fact, each instruction has a count, it is its latency, and each cycle, this count is decremented. So how do you, previously I have said that the instruction set of victims were chosen in a non-deterministic way. Here it will become deterministic because the subset of instruction chosen will be those instructions with their count equal to 0. So this is how the model becomes deterministic. So our choice is deterministic, then the move is deterministic, and then our, I like to say that our model is by construction deterministic because we have composed functions. So now I'll try to present the generic architecture model. So this is important because all what we are going to present after the control is based on this generic architecture model. So this generic architecture model, we have a prefix, then we have the functional units that we call here split nodes, that is a function, and then we have the join node or the commit stage, and then we have suffixes before the last stage of the pipeline, that was the post pipeline. So this is a generic architecture that we can instantiate, and of course, especially with respect to we have instantiated it with the architecture of the hardware team. So this is how we have formalized this generic architecture with other properties, of course, etc. What is important here is a point that is related to the model that will be implemented. The problem is that at the specification level, we reason with instruction numbers, okay? However, these instruction numbers will not be available at implementation time because the instruction numbers are not bounded. So you cannot have at the implementation something that is not bounded. So you have to devise how we are going to bound this instruction number, and you have also to show the correctness between the specification level where we have instruction numbers and the implementation level where we don't have any more instruction numbers. And how have we done this? In fact, we devise for each instruction what we call its root, and the root of an instruction, what is relevant to this root, is only at the bifurcation, the splitting or the bifurcation nodes, we must know where the instruction has to go. So instead of having for each instruction its number and its path, we have only this information. For the moment, we have the at fork, which branch is taken at the fork stage, and at the join, which branch is taken at the join stage. So then what happens at each cycle, a move along the pipeline is done, and this moves, in fact, is a global operation, because when you have to move, you have to see in front of you if you can move. But in front of you, this node has to make the decision if he can move also, so he has to see in front of him. So this is a global operation or a recursive operation. The decision to move is a recursive operation. And the basic papers by Rennecke and Hahn and by the architecture team rely on the so-called will-be-free procedures, that is a recursive procedure, and it is a forward procedure. What we have done, and this is one contribution of our work, is that we can consider that we have unwind this forward call, and if we unwind this forward call, instead of going from left to right, the unwinding gives us how to go from right to left, and we don't have to accumulate the recursive call, and we done this in one pass from right to left. Of course, in order to do that, we have to, as I have said at the join stage, we must give the order that was given at the fork stage, and this is done thanks to, in hardware, this is what they call the scoreboard mechanisms. It is a mechanism that allows you to recover the initial order that the initial instruction of the initial order of the instructions at the entry of the fork stage. What we have for this, we have an input reorder counter and an output reorder counter, and what we do is that at leaving, thanks to the output reorder counter, we know which instruction should leave. And once the instruction left, we increment this counter. And in the same way, at the entrance, each instruction gets its own ticket, and this ticket will be used to reorder the instruction at leaving at the commit stage. Okay, so now this was about the mechanism. What about the properties that we have talked about in the beginning? So we have some, well, I'd say critical properties. For instance, the instructions, we must have a partition of the instruction over the stages. That is, all the instructions must be distributed over the stages, and we must not have instruction in two different stages. This is the instruction partition. The property that all the FIFO are bounded, and well, this is easily expressed in TLA, as well for the memory access property, the mutual exclusion about accesses over the stages. So this is, what I have said, critical properties. But the one interesting property is about the correctness, about the flow of the instructions. what happens is that here from pre to fork until the join, things must be ordered as they were in the beginning. That here things must happen as there was in the initial pre-stage. And we reconstruct this order as follows from pre to fork. So here there is no split, so the order is natural. But here, since we have split and these stages operate in a concurrent way, we must be able to reconstruct the original order. So in fact, here we have a shuffle of the instructions over these different stages. And in order to unwind, if we want, this shuffle, we use the counter numbers that have been given by the scoreboard abstraction. And again here we have the concatenate operator of TLA. So we compose these different FIFOs through concatenation. Here this is a shuffle guided by the reorder counters. And here again we have the concatenate operation of TLA. So this is the ordered part of the ordered part of the pipeline. So this is reconstructed in TLA as follows. So we reconstruct the FIFO of the join state, then we unshuffle the FIFOs inside the different split stages, and then we reconstruct through the concatenations the pre-prefix from the state pre to the state fork. We reconstruct these FIFOs. So this gives us a first property, that is the ordered what we have reconstructed in an ordered way. We must obtain it as a subsequence of the initial sequence in the pre-stage. And this gives us the first correctness property of the first basic safety property. Once we have done that, we have not yet finished, because we have to say that the instructions that eventually leave the pipeline are not instructions that have been created by the pipeline, and the pipeline has not lost any instruction that was initially admitted in the pipeline. So this is given by this second conjunction, and here we cannot anymore reason with orders, because after the commit stage we don't have any order, so we must reason with backs instead of reasoning with sequences that preserved the orders. With backs, we preserve only the number of occurrences. We do not lose any occurrence, and we do not create any occurrence. Okay, so, and the last property that we have to verify, or first to specify, is that initially all the instructions were in the pre-stage, and eventually all the instructions must be in the post-stage, and this property must be stable, and we have to check that no instruction remains in a given FIFO of the pipeline. So eventually, for all the stages but the post-stage, all the stages have their FIFO that is empty. All the stages have their counters that is equal to 0, that is a stage has not been interrupted, and all the instructions with respect to the back bag composition that were in the init, that were in the pre-stage, must be at the end on the post stage, and this property must be eventually reached and kept. So to conclude, well, we have developed a TLA plus pipeline model. As I have said, we have a first stage of the work in which we were more concerned by understanding how a pipeline, complex pipeline works, and also understanding how was the basic proof of the protocol of monotonicity. And well, working with the hardware team, we have gained a better global overview of the protocol. Of course, we have appreciated the TLA plus expressive power, but with respect to concurrency, we was not, I would say that we were not fully satisfied. And as I have said also, now we find the proof engineering much more interesting because we have a software model that is, from our point of view, much more explicative and much more understandable. So the proofs are more interesting because the proofs reflect, from our point of view, the basic ideas of why this complex architecture has the good properties. Future work, so we envision to work about more detailed mechanism modeling, especially for the scoreboard. I have said that we have an abstraction of the scoreboard, but in fact, the scoreboard is much more complex, and we would like to go to this complexity, to this implementation level. In fact, in a general way, we want to have a refinement towards the implementation level model. And also, for the moment, we do not reason at the timing level. That is, all our properties are mainly qualitative. We do not reason about quantitative aspects of timings, for instance, the number of cycles, etc. We do not have a logic that is dedicated for such an aspect of the problem, which is also very important. Okay, thank you.